Human Factors Engineering. General Human Factors Engineering, HFE, is the process of integrating human capabilities into the design of products, workplaces, or work systems, plant facility, resulting in effective, efficient, safe, and healthy functioning of human beings. This integration improves operational and maintenance tasks. It should be used as a design tool checklist during the definition phase to ensure HFE considerations are included in the design package. Key points. Operator tasks are matched to human capabilities. HFE should be part of the design program from the start, with user participation required. Design reviews should be held during various phases to avoid subsequent modifications. Early inclusion of HFE contributes to safe, efficient, and comfortable control of plants without raising lifecycle costs. Background. The use of distributed control systems, DCS, has changed operator tasks in refineries and the chemical industry, making them more supervisory. This shift, coupled with the greater complexity of plants and control systems, has increased operator responsibility. Human error can have serious consequences for productivity, safety, and the environment. Research on human-machine interface design in existing control rooms has identified problems that hinder safe, comfortable, and effective control of automated systems. Main deficiencies found: user complaints about control room layout and furnishings, e.g. console dimensions, noise level, lighting, inefficient walkways. Poor presentation of information on VDU, lack of standardization of VDU layout, color, and symbols. Issues with operators processing information from the alarm and annunciation system, particularly the number of alarms and their confusing presentation. Dissatisfaction with the training accompanying the implementation of DCS systems. HFE in design. Points for consideration. HFE should be incorporated into the design process. The design should consider implications for operational or maintenance personnel. Design decisions often involve compromises. If optimum HFE solutions are not possible, careful weighing of pros and cons is necessary, especially if limits are exceeded, e.g. physical or mental load limits. Prototypes, mock-ups, or scale models and design reviews are valuable methods for checking and adjusting design aspects, such as accessibility, range, and layout. Inclusion of operations and maintenance in the design process is critical for successful HFE design. User participation. User participation should be ensured during all design phases by including operators in the design new construction teams. Operator representatives should be involved when compiling design requirements for aspects like operator philosophy, control room layout, operator console design, DCS design, and engineering and commissioning. Costs, benefits of HFE. Incorporating HFE principles in design enhances effectiveness, reduces human error, and improves design acceptance by operators, leading to lower lifecycle costs. Advantages of HFE. Improved maintainability of control rooms, maintenance tasks take less time. Improved operability of equipment, reduced physical and mental load on employees, reduced occurrences and consequences of human error, fewer machine failures, reduction of modifications, standardization, enhanced quality of work, well-being, reduction of prolonged sick leave and permanent disablement. Console configuration. Future expansion should be considered when determining the console configuration. The configuration of plant layout consoles in the control room should conform to the course of the process, from left to right, especially for alarm displays. Consoles should be grouped functionally for each part of the process. Mirror image layouts should never be used for identical processes. Console arrangements for different processes or parts of processes should be clearly separated. Consoles should be located to avoid annoying reflections on the screen. The lighting plan should be drawn up after the console layout is determined. Arrangement of consoles next to one another or at right angles in a U-shape or C-shape depends on the number of operators and the functional relationship between process parts. Each arrangement has specific pros and cons. The maximum number of VDUs an operator can manage in an upset situation is 3. Determining the console configuration. Further guidance on control desks is provided in relevant standards. Space required for the control room. Determined by space needed for console configuration, peripherals, other workplaces, files, number of operators, meetings, and administration. Space for consoles. Space needed includes the area of the console configuration, space behind VDUs for maintenance, space for VDU operation, partitions, overview, and expansion. Hashed layout of other workplaces. Workplaces in the control room should be equipped for administrative work, checking of drawings, meetings, etc. The furnishing of these workplaces should take account of their functions. Visual partitions should be present between various workplaces, with the console visible at all times. Workplaces should not be located near ventilation grids. In small control rooms, measures should be taken to avoid a shut-in feeling, e.g., vertical glass strips, windows, wall decoration. In large control rooms, measures should be taken to reduce noise levels and enhance speech audibility. Computers and peripherals, due to noise and heat, should be installed in a separate area as far as possible. Windows. Control rooms should have windows to provide a view of the plant and admit daylight. People working in rooms without windows may feel shut in. Windows should have effective sunshades to achieve desired luminance ratios and reduce reflections on VDU screens. Care should be taken to avoid annoying reflections on screens and ensure luminance ratios comply with relevant standards. Transparent partition walls are also permitted. Daylight openings and outside view openings may be subject to statutory minimum dimensions. For example, the area of light openings should be 1/10 of the floor area. The total width of light openings should be 1/10 of the perimeter of the area. Workstation layout. Dimensions and shape. If a graphics panel with alarms is installed, this panel shall be placed above the VDU. The workstation layout shall have a separate keyboard, which, when pushed back, allows room for writing. For furniture requirements and dimensions, see the section on furniture. Logbooks and other necessary documents should also be taken into account. Workstation configuration. The VDU with the most important process information should be positioned straight in front of the operator. Information on screens should be comparable in a horizontal direction. To improve the overview across several screens, workstations should be set up at angles of 10 degrees. The configuration should include sufficient writing space for the operator. Environmental factors and furnishing. Air conditioning. Control rooms contain a large number of VDUs relatively close together. VDUs generate considerable amounts of heat, and their impact on air conditioning requirements shall be taken into account at an early stage in the design. For further information regarding air quality and indoor climate, see the relevant sections. Light and outside view. The lighting plan, based on the control room layout, locations of consoles, workstations, etc., should be produced at the earliest possible stage of the design. The illuminance at the work surface should be between 200 LX and 500 LX. The illuminance shall be adjustable by means of a dimmer and should be controlled from the console. If color VDUs are used, information luminance 20 CD mi Huerta, the maximum horizontal illuminance shall be 320 LX. The luminance ratios between the viewed object, the immediate environment, and the periphery shall be in the ratio of approximately 10:3:1. Light fittings shall meet specific requirements to prevent disturbing reflections on the screens, including deep reflector fittings with plastic or metal mirror grids, screening grids limiting lateral light emission to approximately 40 degrees relative to the horizontal, and equipment of type HF, high frequency, approximately 28 kHz. The color temperature should be between 3300 K and 4000 K. For limited daylight entry, 3300 K. For daylight in combination with artificial light, 4000 K. The color reproduction index RA fluorescent lamps should be at least 83. Noise. Maximum noise levels in control room areas are specified for different zones, with control rooms having a preferred maximum of 40 BA. Noise sources that could disturb voice communication, such as the cooling fan noise of VDUs and acoustic alarms, should be controlled. Measures for controlling airborne and contact sound transmission should be considered since control buildings are located near plants. Materials and color. Color of the room. Fairly inconspicuous colors should be chosen, particularly for large areas like walls and ceilings. Ceilings should be light-colored, walls somewhat tinted, and floors dark-colored. Diffuse reflection values are recommended for specific surfaces to ensure proper luminance ratios. Materials. Materials should consider acoustic properties, light reflections, temperature, and should generally be anti-static. Floor coverings should facilitate the easy movement of office chairs and be easy to clean. Specific requirements govern the choice of materials for furniture. Furniture. Desks should be at least 1200 millimeters wide, 1500 millimeters if a VDU is used, height adjustable between 620 and 820 millimeters, and provided with an integrated cable duct system. The depth of the reading work surface should be at least 600 millimeters, and the VDU work surface at least 900 millimeters. It should be possible to angle the VDU work surface relative to the reading work surface L configuration. Chairs. Chairs should be swivel types, height adjustable, with a flat seat and adjustable backrest. The backrest should be high and adjustable in height, with short adjustable armrests. The chair should have a tilting mechanism lockable in 3 positions and rest on 5 points, sturdy enough for continuous use. VDUs and controls. VDU screens. VDU screens include normal CRT, cathode ray tube type monitors, as well as flat panel screens. Resolution. Screens should reproduce at least 1024 pixels by 1024 pixels for displaying graphic symbols. Anti-reflective coating. The reflection factor should be approximately 0.5%, achievable with a core lambda coating. Image refresh frequency. For screens with dark symbols against a light background, a frequency of at least 70 Hz is needed to avoid flickering, especially important for multiple users using multiple VDUs. Image polarity. Screens with dark symbols against a light background are preferred for better luminance ratios. Screen luminance. This should be adjustable. Noise. Noise produced by the VDU shall not exceed 55 dB, preferably 45 dB. Hack controls. Speed of operation and response. Control activity, e.g. closing valve, 0.1 seconds. Simple instruction, e.g. calling up display, 2 seconds. Complex instruction, e.g. calling up trend, 5 seconds. Error message directly following end of input, 4 seconds, preferably 2. Request for the next page, 1 second, preferably 0.5. If the maximum response time cannot be achieved, the operator should be notified of the expected response time to avoid unnecessary repetition of control actions. Operating stereotypes. The relationship between control operations and resulting movements should correspond with familiar patterns for local staff. For example, turning a knob clockwise should move the corresponding display pointer clockwise. Presentation of information. Introduction. Experience has shown that DCS designers use different principles for symbols, colors, and layouts, leading to confusion if several control systems are integrated into a single control room. Excess auditory and light signals can adversely affect their attention-drawing function. Correct layout of displays is just one condition for an ergonomically acceptable DCS control system. Alarm management and alarm presentation are also crucial. Collaboration between instrumentation engineers and operators is essential for correct pictorial layout. Experienced operators' input and compliance with HFE guidelines for layout and symbols are vital. Cursors. Cursors should not hinder the reading of other information and should flash only if immediate action is required. Cursors should be easy and quick to move, and this agility should be controllable by the user, especially useful for users with limited dexterity. Coding of visual information. Coding methodology should be consistent and redundant for crucial information points. Coding should be used when rapid processing is needed. Available coding methods. Color. Used redundantly with other coding forms. Brightness. No more than 2 levels, clearly differentiable at maximum screen brightness. Reverse video. Used for speeding up retrieval tasks by inserting words or codes in blocks with reversed contrast. Blinking, used if supplementary coding is needed and direct action is required, limited to 2 different flash rates. It should be possible to switch off blinking. Size, no more than 3 different sizes of shapes or characters should be used. Alerting by auditory signals. No more than 2 different auditory signals should be used. 1 continuous signal with adjustable volume, at least 15 dBA above background noise level, shall be produced. 1 intermittent signal for high-priority alarms with adjustable duration and volume, at least 15 dBA above background noise level. Design procedure for visual display information. Operators are often presented with confusing screen information. Inconsistent and insufficiently intelligible layouts and coding can lead to misinterpretation. A wide range of symbols, colors, and visual signals can adversely affect attention attraction, efficient process control, and increase the chance of costly mistakes, especially during upset situations. This situation is termed an interface mismatch. A systematic integration of the operator's information needs in the design process, especially during upset situations, is recommended. The visual display design procedure includes: Step 1. Understanding how operators view the process and the relationships they distinguish. Step 2. Determining the necessary information for a good overview and its display method. Step 3. Integrating the results into a prototype. Step 4. Evaluating the redesigned graphic compared to the old one through typical interface activities.